Alright, welcome back. This will be my last lecture. I'll talk about the other Calabi conjectures, and at the very end, in the last slide, I'll give a very high level overview of what the proof would look like. I don't think I'll do the proof because that would require too much time. Mustafa asked me to show my face in this lecture, but unfortunately I'm unable to record the lecture and show my face. It's a little tricky, so perhaps the next time. Yeah? Alright. So the last time we defined Kahler manifolds. What are Kahler manifolds? They're complex manifolds with compatible Riemannian metrics such that the associated 1-1 form is closed. Equivalently, they're simply such complex Riemannian manifolds having holomorphic normal coordinates around every point. Yeah. Now, not every complex manifold has a Kahler metric. For instance, the Hopf surface does not. But we gave examples of manifolds that do admit Kahler metrics, like tori with a flat metric or CPN with a Fibonacci metric. Any submanifold of CPN will also have a Kahler metric. You just restrict the Fibonacci metric, Cn, and so on and so forth. Yeah. More generally, if you have a positive line bundle, meaning a holomorphic line bundle with a metric whose curvature is positive, that gives you a Kahler manifold. I mean, that brings us to the second thing. We define, given a holomorphic vector bundle and a Hermitian metric on it, we define the Chern connection by writing an explicit formula. We looked at the curvature of the Chern connection. We saw that for line bundles, the curvature is an imaginary 1-1 form. We multiplied it by square root of -1 over 2 pi to get a real 1-1 form. That's the first Chern class. Why the 2 pi? We just glossed over it. Don't worry about it. Okay, the point is the first Chern, the curvature times square root of -1 over 2 pi is a closed form. It's a globally defined closed form. And its Theorem cohomology class is independent of the metric chosen. Okay, so it defines a well-defined cohomology class associated to the line bundle. Okay, the same sort of a construction can be done for vector bundles. Okay, so we looked at the first Chern class. Finally, we were able to state the Calabi volume conjecture, which is simply given a positive top form, is it a volume form? Yeah. So that gave rise to a second order nonlinear PDE called the complex Monge pair PDE. Yeah. All right. So let us define a special line bundle on complex manifolds. So if M is a complex manifold, you have the holomorphic tangent bundle, you have the holomorphic cotangent bundle, but these are not line bundles, right? How do you create a one-dimensional vector space out of a given vector space? Take the top exterior power, that is one-dimensional, right? So the top exterior power of the cotangent bundle, namely the bundle of n0 forms, that's a very important line bundle. It's given a name. It's called the canonical bundle. It's denoted by Km. It's not obvious as to why that it would be important. I don't think I can really convince you of that unless we go into a lot of details about algebraic geometry. But let's see. I hope by the end of this lecture you'll be able to appreciate why we care about the canonical bundle, at least a little bit. By the way, it's dual, namely the top exterior power of the holomorphic tangent bundle is called the anti-canonical bundle. Just terminology. If the dimension of M is 1, by the way, such manifolds are called Riemann surfaces, complex one-dimensional compact complex manifolds are Riemann surfaces, and by the way, they're all projective. Okay. It's not easy, it's a theorem of Riemann. In such a case, Km is simply just the cotangent bundle. Okay, it's just a special case. Alright. Okay, so recall that if you take CPN, we have an explicit local formula for the Fibonacci metric. Once again, when it comes to a Kahler metric, or for that matter even a Hermitian metric, the information about the metric is conveyed completely through its associated 1-1 form. So it is very common in Kahler geometry to refer to the 1-1 form itself as the metric. Okay. So anyway, so the Fibonacci 1-1 form in the standard local coordinate chart is square root of -1 del bar log of a certain thing. Okay. Alright, so we have an explicit formula. It's a little unpleasant, but it's still explicit. So this gives you, this 1-1 form gives you a Hermitian matrix, right? You can compute the determinant of the matrix, and that determinant induces a metric on the anti-canonical bundle, that is, on the top exterior power of the tangent bundle. 1 over that metric is a metric on the canonical bundle. So its first Chern form is given by this formula. Okay. The bottom line is, all I'm saying is, for this particular metric, you can explicitly compute these things. Okay. When you do that explicit calculation, fascinatingly enough, notice what you're doing is you're computing first. How do you compute the Fibonacci metric? You take two derivatives of a complicated function. You get a matrix, compute that determinant. Already it sounds tricky. Take the log and take two more derivatives. Now, if you do all of that, it's not clear you'll get some pleasant object, but in fact you will. So this Chern form, first Chern form, is simply minus n plus 1 times the Fibonacci form itself. Okay, so that's very pleasant. So it's just a multiple of the Fibonacci form. That doesn't happen all the time. Yeah. It's special for CPN. By the way, there are interesting questions of the type: if the first Chern class is n plus 1 times a certain class, where that class has a certain volume, then can you conclude this manifold is CPN, etc.? There are many such questions. Many of them have already been answered. Okay. Alright. So, CPN is fine. How does one come up with examples of submanifolds of CPN? One takes one's favorite degree D polynomial, sets it to 0. Not quite a favorite degree D polynomial. Its gradient should also be non-zero throughout the 0 locus. So such polynomials define smooth submanifolds of CPN, right, of dimension n-1. So suppose you take such submanifold, then it's a Kahler manifold. Why? You can restrict the Fibonacci K metric to get a Kahler metric. Yeah. Now in principle, you can take this Kahler metric, compute its determinant, take log of that, and compute del bar of log of that. So that will be a very tricky calculation. But if you do that, you'll get a very pleasant conclusion. The calculation is tricky, it's not trivial. So the conclusion is, the first Chern form of the canonical bundle of the submanifold is D minus n minus 1 times the Fibonacci metric plus del bar psi. So in other words, at the level of cohomology, it's simply a multiple of the Fibonacci metric, Fibonacci Kahler class restricted to the manifold. By the way, if you find it difficult to do this calculation, it's there in a paper by Liu called the Bando-Futaki invariants of hypersurfaces. Sorry, there's a typo there. And this cohomology class calculation can be done even without any differential geometry. It can be done using algebraic geometry if you know what the adjunction formula is. Yeah. But you don't need such fancy tools. This can be done in a very hands-on manner. Okay. All right. So recall that if you take a holomorphic vector bundle, its first Chern form is the same as the first Chern form of its determinant bundle, line bundle, right? So the first Chern form of the manifold S is the first Chern form of the anti-canonical bundle, which is negative of the first Chern form of the canonical bundle. Okay, so it's just negative of the previous formula. Now we'll notice something very fascinating. Okay, so take the anti-canonical bundle. It already has a metric. What's the metric? The determinant of the Fibonacci metric. You multiply this metric by a smooth function. This particular smooth function, e raised to 2 pi times psi, where psi is the function coming from this formula. Yeah. If you compute the first Chern form of this metric, then you will get, sorry, I should have written this more clearly. The first Chern form of this metric is simply n plus 1 minus d times omega fs. As a consequence, if d is very small, the first Chern form of that metric is positive. So the anti-canonical bundle is a positive line bundle. If d is very large, d is larger than n plus 1, then it's a negative line bundle. For d equals n plus 1, the first Chern class is 0, right? Such manifolds having first Chern class 0 are given a name. They're called, I'll come to the name soon, but here's an example of a threefold in CP4 which satisfies the first Chern class being 0. Why is the first Chern class 0? Because d here is 5, n is 4, so d equals n plus 1. So such manifolds are called Calabi-Yau manifolds. Okay, they're very important in string theory. Here's a very quick overview of what string theory is about. So the universe, according to Einstein's general theory of relativity, is a four-dimensional manifold. It's called space-time, right? 3 directions of space, 1 of time. Unfortunately, this doesn't play well with quantum mechanics. So one proposal to unify relativity and quantum mechanics is string theory. Well, whatever string theory is, there are many versions of string theory, by the way. One of its versions, superstring theory, a kind of superstring theory, implies that the universe is not a 4-dimensional manifold, it's actually a 10-dimensional manifold. Well, where are the other 6 dimensions? We can't see any of them here, right? So the idea is that actually it's our usual 4-dimensional space-time cross a 6-dimensional compact manifold, having a very small volume. So we are like ants walking on a string. We think it's 1-dimensional, but in reality it's actually 3-dimensional, right? A string. So that's how the 6 dimensions are hidden. So these compact manifolds, under certain conditions, are expected to be Calabi-Yau manifolds. That's the connection. Okay? Alright, so let's deal with connections, curvature, etc. on Kahler manifolds. So suppose you have a complex manifold with a Hermitian metric, not yet a Kahler metric. It induces a compatible Riemannian metric, we already know this. There are 2 connections on the holomorphic tangent bundle. One is the Chern connection of H, which we discussed the last time. Notice that the holomorphic tangent bundle is isomorphic to the real tangent bundle using a standard isomorphism, and I said that I'll always identify these 2 bundles with that isomorphism without mentioning it. Yeah, this is one of those times, for instance. So there's this Levi-Civita connection of the associated Riemannian metric on the real tangent bundle that induces a connection on the holomorphic tangent bundle. So there are 2 connections on this bundle. Okay. So natural question is, when do they coincide? Okay. So if M is scalar, these 2 coincide. Now that seems like a formidable statement, right? It seems to require you to compute these connections and see if it coincides, if d omega is 0 and so on. But actually there's a shortcut to prove this, and that's as follows. Suppose you want to prove that these two connections coincide at a point P, right? Now if their expressions coincide in one coordinate system, they coincide in all coordinate systems. So choose holomorphic normal coordinates. They exist because M is scalar. What is the meaning of the phrase holomorphic normal coordinates? Omega, G, H, all of these are standard up to first order. That is, they are all Euclidean, and the first derivative is 0 at that point. Meaning, both kinds of Christoffel symbols, the ones coming from the Levi-Civita connection as well as the ones coming from the Chern connection, they're both 0 at that point in these coordinates. Hence, they coincide. So we're done. Right? So it's easy to prove that if M is scalar, these two coincide. The other way around is also true, but this sort of a shortcut doesn't work. You have to do a little more work. Okay? In any case, what's more important for us is this direction, right? If you're Kahler, then these two coincide. Why is it so important that they coincide? Because we know a lot about the Levi-Civita connection. I'm assuming you know Riemannian geometry, so you would have seen several theorems of Riemannian geometry, right? For instance, if all the sectional curvatures are constant, then we know the topology. If the Ricci curvature is bounded below by a positive number, we know the topology, and so on and so forth, right? We know something about the topology in that case, and so on, right? So there is no similar geometry for the Chern connection. So on the other hand, the Chern connection is easier to compute, right? So it is crucial that these two coincide, because now you can link computations and analysis to topology. So you can link algebraic geometry and topology for Kahler manifolds very often. In fact, if they're projective manifolds, it's even better. Okay. Alright, so if M is scalar, the Levi-Civita connection already has many symmetries, but because it's also the Chern connection, it has many more symmetries. Okay, it's crucial, this particular observation. So let's look at the curvature of Kahler manifolds. Yeah. So recall, what is the Riemann curvature tensor? The Riemann curvature tensor for the Levi-Civita connection for that measures the failure for the directional derivatives to commute. So R x y z is nabla x nabla y z minus nabla y nabla x z minus nabla the commutator of x y z. Yeah. But we looked at curvature, connections, etc. when we defined the Chern connection in terms of matrices of two forms, right? Not in this language. How are these two related? It's not rocket science. You see the x and y. If you interchange x and y in the Riemann curvature tensor, you pick up a negative sign, right? So R of xy functions like a two form. So if you take the curvature matrix of two forms and you feed it x and y, you get an honest matrix of real or complex numbers, right? That matrix, when you multiply it with the components of z, you get R, x, y, z. Okay? Right. So recall this very important trace of the Riemann tensor, the Ricci tensor. It's defined as the trace of R, x, y, z over x, right? So now I'm going to play very fast and loose with complex geometry and real geometry. In other words, you recall that there is an isomorphism between the real tangent bundle and the holomorphic tangent bundle, right? You can identify these two bundles by means of that isomorphism. I'm going to do that very often now, and there may be a few factors of square root of -1s, etc. missing. I invite you to do these calculations carefully on your own. keeping in mind that isomorphism. Please do them rigorously. Okay. All right. So Ricci KL. What that means actually is Ricci acting on the partial derivative with respect to k and partial derivative with respect to L, these two vector fields, is simply given by theta IL partial I partial k. That's just when I write an I here, there are two i's, right? You're summing over the two i's. I'm using Einstein summation. So in holomorphic normal coordinates, notice what is the expression for the curvature? It's del bar of h bar inverse del h bar. In holomorphic normal coordinates, the first derivative of h vanishes at that point. H itself is identity at that point. So the matrix for theta is simply del bar del h bar ij. Okay. And since it's Kahler, we know hij is simply the second derivative of the local Kahler potential. Okay. So the curvature is, roughly speaking, just in appropriately chosen coordinates. It's simply the fourth derivative of a locally defined smooth function. Okay, for Kahler manifolds. This sort of a thing does not happen in real differential geometry. Okay, therein lies the magic of Kahler geometry. In these coordinates, you can compute the Ricci tensor to be some combination of those four derivatives. So if you interchange derivatives, you can see this very fascinating thing. You can define a Ricci form, okay, by taking Ricci KL dz k wedge dz L bar. That can be computed very easily by simply taking the trace of the curvature matrix. So the curvature is a matrix of two forms. If you take its trace, you get a two form. That two form corresponds to the Ricci tensor. Okay. The normalized Ricci form is therefore the first Chern form. So the bottom line behind all of these calculations is the first Chern form corresponds to the Ricci curvature of a Kahler manifold. The first Chern form is of highly algebrogeometric quantity. The Ricci curvature is a Riemannian geometry quantity, but it is strongly linked to topology, and hence the link between algebraic geometry and topology. Okay. All right. So here's another Calabi conjecture. This is when people say the Calabi conjecture, they usually mean this one. Okay. All right. So all of Calabi's conjectures are of the form given something, something exists. Okay. So here you're given a real closed 1-1 form eta lying in the first Chern class of the manifold. Okay, so you're given a form, a 2-form eta, roughly speaking, and you're given a Kahler class. In all of Calabi's conjectures, you're more or less all of them, you're given a Kahler class and you're asked to find a Kahler metric in that class satisfying something. So there exists a unique smooth Kahler metric, omega phi is omega plus square root of -1 del bar phi, such that its Ricci curvature is given. So you're given a Ricci form in the correct cohomology class, and you're asking me when the Ricci curvature is equal to this form. Okay? Or rather, find a metric so that this happens. This conjecture has also been solved. This was solved by Yao. So when C1 of M is 0, then you can take eta to be 0 and ask for a Ricci flat metric. In other words, Calabi-Yau manifolds admit Ricci flat metrics. Okay. So in particular, what do we know an example of a Calabi-Yau manifold? Sure we do. Take the Fermat quintic, right? Remember the Fermat quintic? That is, you take a very symmetric degree 5 polynomial and set it to 0 in CPn, in CP4. Yeah. So by the Calabi conjecture's solution, there is a Ricci flat metric on this beast. But for all we know, that metric could be flat, right? Meaning its Riemann tensor, I mean, it's sectional curvatures, its so-called holomorphic sectional curvatures, could be zero. Or in other words, the Riemann tensor itself, for instance, could be zero. If that is the case, then it's a very trivial example, right? See, if I ask you to find an example of a Ricci flat metric, there is an obvious example. Just take your favorite torus, it has a flat metric, so hence it is Ricci flat, right? Can you find any other examples? Until Yao came to the scene and solved the Calabi conjecture, there were no examples as far as I know. Okay. So the Fermat quintic does have a Ricci flat metric, but how do you know it's not flat? If it is flat, one can prove using, I think, it's called the Killinghopf theorem, that this manifold is actually isomorphic to a torus if it is flat. However, one can show that Q5 is simply connected. This follows from the fact that CPN itself is simply connected. Yeah, and that the simple connected behavior descends to hypersurfaces. This can be done using Morse theory, for instance, or the Lefschetz hyperplane theorem. Anyway, the bottom line is, thanks to some standard algebraic geometry or topology, you can show that Q5 is simply connected. Therefore, it cannot be a torus. Yeah. So this is the first such example. Yeah. Now let me give you another application of the Calabi conjecture. If C1 of M is positive, what does it mean for a class to be positive? That means it has a Kahler form in it. Okay. Then you can choose eta to be a positive form. So in other words, the Calabi conjecture implies that there is a positive Ricci metric. In other words, the Ricci curvature of such a metric is positive. Therefore, remember Boni-Myers from Riemannian geometry. The Boni-Myers theorem asserts that if the Ricci curvature of a compact manifold is positive, then its fundamental group is finite. Actually, what it says is if the Ricci curvature is bounded below, then the diameter is bounded above, so the manifold itself is compact. But if your manifold has Ricci curvature bounded below, the pullback of this metric to the universal cover also has Ricci curvature bounded below, so the universal cover is compact and hence the fundamental group is finite. In other words, if the first Chern class is positive, which is something that can be checked through algebraic geometry, the fundamental group is finite. Okay, so algebraic geometry implies some topology. In fact, you can use some more algebraic geometry to show that these manifolds are actually simply connected. It's not just that the fundamental group is finite, it's trivial. Okay, such manifolds are called Fano manifolds. So Fano manifolds are simply connected. There are other proofs of this statement also, but the Calabi conjecture provides an elegant proof. Yeah? Right. So these are some applications of this particular Calabi conjecture. Alright, so the Calabi conjecture a priori is a fourth order PDE. Why? Because omega phi involves two derivatives of phi. Ricci involves two derivatives of omega phi, so it's a fourth order PDE in phi. But thankfully, we can actually reduce it to a second order PDE. So firstly, note that eta, suppose you take any metric omega in this scalar class, let's call it omega, its Ricci form is not equal to eta. If it was, then we would have been done, right? However, these two are in the same cohomology class, so by the del bar lemma, their difference is del bar of some function, right? So, the Ricci of omega phi, which we want to be equal to eta, is eta minus Ricci omega plus Ricci omega, so it is equal to Ricci omega plus square root of minus 1 del bar f. But what is the Ricci curvature? it's square root of minus 1 del bar del log determinant of the metric. So in other words, square root of minus 1 del bar log determinant of omega divided by determinant of omega phi, which is the same thing as omega raised to n by omega phi raised to n. Remember the volume forms of a Riemannian manifold and the relation between that and omega raised to n. It's the same calculation. Yeah? So, omega phi raised to n. So what this is saying is del bar of something equals del bar of something else. That means the difference of these two is a constant, as I mentioned a lecture or two ago. Okay. So the bottom line is omega phi raised to n is some function times omega raised to n, such that the integrals on both sides are equal. But we recognize this equation, don't we? It is simply the complex Monge-Ampere equation encountered in the volume conjecture. Okay, so the volume conjecture's importance stems from the fact that this Calabi conjecture can be reduced to that. Okay. Alright, so as I said, there are several Calabi conjectures. So we stated the volume conjecture and the representability of the first Chern class conjecture. The next one has to do with Kahler-Einstein metrics. Okay. So in general relativity, which is due to Einstein, it attempts to model the universe, the gravity of the universe. So according to that, the universe is a four-dimensional Lorentzian manifold. Lorentzian simply means that the signature of the inner product is not Euclidean, it's minus 1, 1, 1, 1. Okay. So it's a Lorentzian manifold, space-time, and the metric satisfies Einstein's equations. Okay. The metric tells us about gravity, and it satisfies Einstein's equations, which are Ricci g is lambda g plus some tensor rho. That rho has to do with matter and energy. Okay. And this lambda is related to the cosmological constant. It's related to the so-called dark energy. So in vacuum, Ricci g equals lambda g. So such metrics are called Lorentzian Einstein metrics, but we are interested in such metrics even in the Riemannian category. Okay. In particular, in the Kahler category, a Kahler-Einstein metric is one that satisfies Ricci omega's lambda omega. So in particular, the Ricci form represents the first Chern class. Right? So lambda has a sign, either it's 0, positive or negative, meaning the first Chern class of a Kahler-Einstein manifold has a sign. So not every complex manifold can admit a Kahler-Einstein metric. Its first Chern class better have a sign. So if the first Chern class is positive, lambda is positive. If it's Khalaby, lambda is 0. If C1 is negative, then lambda is negative. Yeah. So the third Khalaby conjecture is, if C1 has a sign and you normalize lambda so that it's 0, 1 or minus 1, there is a unique Kahler-Einstein metric. Okay. So for C1 equals 0, we already saw that the previous Calabi conjecture solution implies this thing. For C1 less than 0, Aubin and Yau proved this conjecture a long time ago. Yau actually did all of this on one single paper. A very impressive paper. However, and here is the shocking fact, it is false for Fano manifolds, that is for C1 positive. So, the intuition you should have here is the following. If you take surfaces, right, classification of surfaces, remember you have genus 0, the sphere, genus 1 is torus, and genus g greater than or equal to a connected sum of tora. On the sphere, by the way, all surfaces have a complex structure and they are all Kahler. Okay. The complex structure is not very hard. All orientable surfaces having a complex structure is not rocket science. You simply rotate anti-clockwise by 90 degrees, as I mentioned earlier. Why are they all Kahler? Because any two form is closed, so omega is closed. Okay, so they're trivially Kahler. And the uniformization theorem implies that they all admit Kahler-Einstein metrics. The sphere has an obvious one, the round metric. The torus has an obvious one, the flat metric. Genus G greater than or equal to 2, they're all hyperbolic. Okay, they're negatively curved metrics. Notice that most of them are actually negatively curved. Only one of them is positively curved, the sphere, right? This sort of phenomenon persists even in higher dimensions. The C1 greater than 0 case has very few, not very few, but far fewer examples than C1 negative. So for most of the cases, this conjecture is true. But it is false for C1 positive in general. Okay. There are obstructions, as in you can clearly quantify when it is true and when it is not by means of an obstruction that is related to algebraic geometry. It's called K-stability. Okay. Now all of that, a complete understanding that K-stability is equivalent to the existence of a Kahler-Einstein metric on Fano manifolds was available only since 2012, whereas Yao and Aubin did their work a billion years ago. Yeah, and so this conjecture that K-stability, whatever that means, is equivalent to the existence of a Kahler-Einstein metric on Fano manifolds is called the Yao-Tian-Donaldson conjecture. And this complete understanding was provided by lots of people. The theorem was proved building on the work of a lot of people, and there were several different proofs of it also. So, I mean, unfortunately, I can't list down all the people who have worked on it, but some principal names are Yao Tian Donaldson, Chen, Shushong Chen, Sun Song, Ved Datar, Gabor Sekilhiti, Berman, Buxom Janssen, etc. Okay? Alright, so that's that about Kahler-Einstein metrics. But notice, a priori, this is also a fourth order equation, right? Thankfully, this also reduces to a second order PDE. How? So let mod lambda be equal to 1. We've already covered the lambda equals 0 case. Alright. So first of all, you take any old metric omega. If it already is Kahler-Einstein, you're done. If it's not, lambda omega minus Ricci omega, the cohomology class of lambda omega and Ricci omega is the same. So lambda omega minus Ricci omega is square root of minus 1 del del bar f. So we want Ricci of omega phi to be lambda omega phi. So when you simplify and the dust clears, you'll get this. Okay. So as a consequence, you see omega phi raised to n is almost like the volume conjecture. Some function times omega raised to n times e raised to minus phi, minus lambda phi. Seems like a very minor modification of the volume conjecture, but shockingly it behaves very, very differently when lambda is positive. Okay, when lambda is plus 1. Okay, so this can also be reduced to a second order PDE. These equations are also sometimes called Monge-Ampere equations. If lambda is minus 1, actually the lambda equals minus 1 is the easiest case out of all the Calabi conjectures. Okay. Just to demonstrate that it's the easiest case, I'll prove uniqueness for you. I didn't prove even uniqueness so far, right, for any of the Calabi conjectures. We can do that here. Suppose there are two solutions, that is, suppose there are two metrics such that Ricci of both the metrics, such that both metrics are Kahler-Einstein. Okay. So call one of them omega, the other omega phi. So if omega is Kahler-Einstein, then lambda omega minus Ricci omega is 0. So in the first line, f is 0. Yeah. So substituting that into the equation, we see omega phi raised to n is e raised to phi omega raised to n. So at the maximum of, oh, I'm so sorry, there's a typo. At the maximum of phi, it doesn't make sense to talk about the maximum form. You can talk about the maximum of function. The maximum of phi, what happens? Calculus tells you that the first derivative is 0 and the second derivative is negative definite, right? Or at least non-positive definite. So as a consequence, del bar phi is a negative definite Hermitian matrix. So omega plus del bar phi is less than omega. Okay? So omega phi is less than omega at the maximum of phi. But omega phi raised to n, which ought to be less than omega raised to n, is equal to e raised to phi omega raised to n. Meaning phi is less than or equal to 0 at the maximum. So phi is less than or equal to 0 everywhere. Likewise, using the same philosophy at the minimum, we see phi is greater than or equal to 0 everywhere, so phi has to be equal to 0. This philosophy of calculus, that at the maximum of a function, the second derivative is negative, this trivial observation is called the maximum principle. Okay. This technique is very useful, and Yao used this technique over and over again in his proof. Okay. Alright, so that's Kahler-Einstein metrics. Now let's go to far more general metrics. The constant scalar curvature Kahler metrics, CSCK. Okay. So before we go to that, what's the point of studying Kahler-Einstein metrics? Why do we have to bother about the Calabi conjecture for Kahler-Einstein metrics? We already saw why to bother about the second Calabi conjecture. We already saw two applications. The Kahler-Einstein metrics, it's a little harder for me to convince you why you should care about them, because you need some more prerequisites for that. The point is, if there is a Kahler-Einstein metric, there are inequalities between Chern classes. We saw the first Chern class of a manifold, right? Akin to that, there are higher Chern classes too. They can also be computed using algebraic geometry. And if there is a Kahler-Einstein metric, there are inequalities between the first and second Chern classes. And there is an inequality called the Bogomolov-Miao-Kayao inequality. And we already know that there is a Kahler-Einstein metric, for instance, when C1 is less than 0. So if C1 is less than 0, you have an inequality of Chern classes. So that severely constrains the topology and the algebraic geometry of such manifolds. Okay. The other thing is, one can construct moduli spaces of manifolds admitting Kahler-Einstein metrics in an analytic manner. If you don't know what this phrase means, ignore it. But that's another point. Unfortunately, if C1 of M does not have a sign, right? If C1 of M does not have a sign, then you can't have Kahler-Einstein metrics. But can we find some standard nice metric in that class, even if there is no sign, or even if C1 of M has a sign but omega is not in that class, right? So that's an interesting question. So what kind of classes are we looking at? For instance, if you take any line bundle which is positive, its first Chern class can be such a class. Yeah. So why would you care about that question? Once again, moduli spaces. If you take positive line bundles L on complex manifolds M, if this question can be answered, that you can find a standard unique metric in C1 of L, that means the set of all such pairs is parametrized by the set of all such metrics, right? So that can help, all right? So one PD that attempts to achieve this objective is the constant scalar curvature Kahler PD. So recall that the scalar curvature is just the trace of the Ricci tensor. In Kahler geometry, it's given by a very concise expression. It's simply the same thing, but you can write it in terms of forms. Okay? Please do it as an exercise to see that these two are one and the same. Okay? By the way, the scalar curvature in Kahler geometry is not exactly the scalar curvature in Riemannian geometry. They differ by a factor of 4 depending on your conventions. Okay, so just be a little careful. Alright. So yet another Calabi's conjectures is the existence and uniqueness of CSCK metrics. Okay. Now Kahler-Einstein metrics already have constant scalar curvature. That is trivial. Okay. But we want to find CSCK metrics in general. Okay. This question is still open. In its full generality, no one knows the answer. We know the answer in special cases, not just Kahler-Einstein, but several other special cases. But they're all very hard. Okay, none of them is easy. So spectacular developments were made by Donaldson in the toric case. Toric varieties are very special, very symmetric complex manifolds. They're nice testing grounds for various conjectures. Donaldson, and based on his method, lots of other people also worked on it. Then Tamás Darvas and Yanir Rubinstein, they came up with characterization of CSCK metrics using the Mabuchi functional and so on. Then Shushong Chen and Cheng, I believe the topic of one of the lecture series in this workshop is Chen Cheng's work. They made some more spectacular analytic developments. Okay, there are lots of other developments. I'm sorry, I'm skipping many of them. But yeah, this question is still fully open. Okay. Of course, we can ask one more natural question. Why pairs? Why not triples? M, L, and E, where E is a holomorphic vector bundle, right? So the correct PDE for that moduli space was discovered by Mario Garcia Fernandez, Luis Alvarez Consul, and Oscar Garcia Prada. And it's called the Kahler-Yang-Mills equations. Okay. That is still in its infancy. The very few results known. I mean, sorry for the shameless promotion, but with these three authors and with Chengji and Yao, I also contributed a little bit to this. But this area is still in its infancy. All right. So I'll end with a very high level proof of the volume conjecture. Okay, this is at a very high level. Obviously the difficulty lies, the devil lies in the details, if you will. Okay. So how do you solve PDE? In particular, how do you solve nonlinear PDE, even if you know how to solve linear PDE? Okay. The one very nice method, it's my favorite method at least, is the method of continuity. Instead of the PDE you're trying to solve, come up with a family of PDE that depend on a parameter t between say 0 and 1, such that at t equals 0, the PDE is a PDE that you can solve. At t equals 1, it's the PDE that you want to solve. And you somehow want to deform the solutions from one to the other. Okay. So consider this particular family of PDE, omega phi t raised to n, is e raised to tf omega raised to n. At t equals 0, phi t equals 0 obviously solves this PDE, right? So there's a solution at t equals 0. We want to solve it at t equals 1. So we want to prove that the set of t between 0 and 1 such that it has a smooth solution is both open and closed. So it will be connected. Since it's non-empty, it should be all of 0, 1, right? So to prove it's open, what does that mean? Suppose you have a solution at t, you want to find solutions for nearby values of t, right? This sort of a question should remind you of the implicit function theorem, right? If you have a function of two variables f of x, y, and if you have a solution at if f of x naught comma y naught is 0, then for all nearby values of y, you have a solution x in terms of y, provided the derivative with respect to x is invertible, right? So akin to that, there's an infinite dimensional implicit function theorem that reduces the problem of openness to the solvability of a linear partial differential equation. Linear partial differential equations are far easier to handle than nonlinear ones. Unfortunately, if you have never seen elliptic PD, it is hard for me to tell you what they are in one slide. All I can say is, if you know the Laplace equation, elliptic PD are like the Laplace equation. Yeah. So for instance, if you want to solve Laplace u equals v on a manifold, you can't always do it. Okay. Just like if you take a linear map between two vector spaces, you can't always solve tu equals v, right? You can solve it precisely when v is orthogonal to the kernel of t star, to the adjoint of t. Right? This is just standard finite dimensional linear algebra. Akin, that same finite dimensional linear algebra intuition carries over to elliptic PD. That's the whole point of ellipticity. Okay? This intuition carries over. But anyway, I'll gloss over this detail, but trust me, this part is actually quite easy. Okay? It's not rocket science. Rocket science, or something more fundamental than rocket science itself, is the next part to prove closedness. What does closedness mean? What does it mean for a set to be closed? It contains all of its accumulation points, right? So suppose Tn is a collection of times for which you have a solution. So for instance, from openness, what you can conclude is that the set of T for which you have a solution is of the form closed interval 0, comma, open interval T naught, right? So it's of the form 0, comma T naught, which is a semi-open interval. You want to prove that T naught is also in that set. So if you have a sequence of times Tn going to T naught, we want to prove that at T naught also you have a solution. Suppose we manage to prove that for each T, for each Tn, maybe I should have said that, phi T, the C2 alpha, what is C2 alpha? The C2 alpha simply means that C naught, for instance, is the supremum of phi. C1 is the supremum of phi plus the derivative of phi. C2 is supremum of phi plus derivative of phi plus supremum of the second derivative of phi. That's the norm. Alpha is the Helder norm, right? Please look it up if you haven't seen Helder spaces. So if we prove that estimate, okay, then you can do it as an exercise to show that by Arzelà-Ascoli, a subsequence of the phi Tn's converge in C2 beta, where beta is less than alpha, to some function. So since this is a second order PDE, all the second derivatives converge pointwise. That means the resulting function solves the PDE. Right? So by Arzelà-Ascoli, if you can prove these so-called a priori estimates independent of T, that is, you assume you already have a solution and prove that the solution is controlled independent of T. Okay, suppose you do that, we have at least a C2 beta solution at T naught. But we want a smooth solution. Now that's not rocket science, that follows from standard theory. Okay, if you have a C2 beta solution, it's automatically smooth. So the difficulty comes in proving these a priori estimates. Okay. How do you prove such estimates? What you do is you first prove that the C0 norm is controlled. Then you prove further higher order estimates. Okay. And the C0 estimate is very different from the higher order estimates. The higher order estimates usually use the maximum principle. You know, the same maximum principle we use to prove uniqueness. The C0 estimate requires some genuinely new ideas. In the case of the volume conjecture, Yau used the Moser iteration philosophy, Nash-Moser iteration technique to prove it. And it is the C0 estimate that fails in the Fano case. Okay. Everything else works. It's just the C0 estimate that fails. So it is met if and only if K stability holds. Okay? Alright, so I hope this lecture series has been useful. So I'll end it here.